recording. Okay. Recursion, we were having a lot of fun last time, so we'll keep having fun. We'll continue on learning a little bit about recursion. Hopefully what we saw last time wasn't terrifying. It shouldn't be terrifying. I mean, the stuff we were looking at was simple. If you were scratching your head, the trick is slow down. What does it mean? Grab your sheet of paper and a pencil, slow it down. If you're still confused, you didn't slow it down fast enough. What does the code say? Follow the code, and then you'll be good. And the only way to get experience with recursion is, or pardon me, the only way to get good with recursion is experience with recursion. So practice, practice, practice. There are some programming languages, like I've shown before in like 161 and during labs, I showed like a programming language, oh my goodness, Haskell, where there's no, like, you're not allowed to have loops. So you can, anything you want to do that loops, you have to do it recursively. And that's a great way to learn recursion, is use a language where you can only do recursion. Although I don't really suggest grabbing Haskell for the fun of it. It's a great language to play around with and everything, but not as practical for many individuals. And it was funny, when I was doing my undergrad, I took a course on Haskell, and it was one of those years in computer science where it ended up being like, that semester, that ended up being the only programming course I had, because all my other courses were like a math class, or maybe like your algorithms where you don't code, or your theory of computation where you don't code, those types of things. So it was funny because I had spent such a long time only programming in Haskell that when I went back to take, I think I took like an AI class after where we were programming in other languages and you would do loops. But it was funny because I legitimately forgot how to, like, wait, how do you loop? Because I was so used to recursion, like that I didn't know. So it's funny because, you know, you get used to loops and then recursion's weird and different. But when you get to recursion, loops are what's weird and different. So anyways, all right, let's carry on in the slides. All right, where did we really leave off? Okay, so we played around with factorial. So iteration is repetition with loops. That should have been not reputation. And recursion is defining something in terms of a smaller or simpler version of itself. In fact, I'm gonna, whatever, I'll do it later because God knows I'm not gonna save it. Recursion is an alternative to iteration. Anything you do with iteration, you do with recursion. Anything you do with recursion, you do with iteration. Though, just because you can doesn't mean you should. Oh my gosh. I had a lot of sleep last night too. Recursion can be used as a programming technique where a function calls itself to solve a problem. A function that invokes itself is called recursive and must contain our base case and a recursive part. I know I've said this like a bunch of times already. It's because this is super important. Like, this is something you put on the exam. Although not this year because the exam is going to be take home. Consider the problem of computing the sum of all numbers between 1 and n inclusively. So if I say 5, I want 1 plus 2 plus 3 plus 4 plus 5. So sum the numbers 1 to 5. 1 plus 2 plus 4 plus 5. Great. Sum the numbers 1 to 5. It's easy to do iteratively, right? There. This code. Look at this code. At this point, you best agree that, yes, this will sum the numbers between 1 and 5. Sum is 0, then have a counter, I, start at 1, go to 5, but include 5, I plus plus, and then just add sum, or add I to sum, and then store it in sum. You do that, we're going to get 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15. So that should give us 15. Now, let's define this recursively. And if you see that this looks similar to factorial, you're right. But here, if we look at this, and for those of you that just didn't spend the time with math, or maybe you forgot, this right here is like the symbol for sum. So this means add all the numbers from k to 1 to n, where n is some arbitrary number. Well, they're saying that, well, the sum of this, which if we put 5 would mean, if we wrote this, k equals 1, and then n, or sorry, we say like 5, this would be equivalent to 1 plus 2 plus 3 plus 4 plus 5. That's what it means, okay? But for fun, let's do it recursively, where we say, well, you know, what if we took the sum from 1 to n and we said, okay, well, instead of doing that, what if we take n and then just add n to the sum of all numbers from 1 to everything up to but excluding it? So basically this is saying like, well, okay, the sum of k equals 1 to 5 k equals 5 plus the sum k equals 1 to 4. Would you agree? If I had the sum of all numbers from 1 to 4, including 4, and then added 5 to it, well, I would have the sum of all the numbers 1 to 5, including 5. That's the idea. So we've basically defined it in terms of itself, recursively. So here's how we do it. So we say, okay, the sum of n to n is n plus this, which is equal to n plus n minus 1, plus the sum of that to n minus 2. So if we plugged it, like if we keep going, we'll just keep going and do n minus 3, n minus 4, 3 to 2 to 1. And here's how I would code this. Recursive sum takes some integer. So imagine this is like the symbol this, okay? I'm gonna say, if n is 1, well, it's, look, the sum of 1 to 1 is 1. That's not a mystery. We know this. There's no magic there. And so if I said, okay, well, if n is 1, 1, otherwise, it's like doing is equal to n plus, and remember, rec sum is like the symbol. So this is like to n here, plus, what the heck? That's not what I wanted at all. Erase. Nope, not a laser pointer. Pen. Plus the sum to n minus 1. I went sideways, but deal with it. See, so like if we think of rec sum as that sum symbol, that fancy E looking thing, then this right here reads just like what we just saw. N plus the sum of up to n minus 1, right? So just replace, like basically control F rec sum with the sigma. That's a sigma, right? Recursion and call stack. So remember, any function method that is called, well, we'll create a call frame, or what else do we call it? A call frame or address, whatever we call it, a call frame, and then we push it onto the system stack. And every time a function calls itself, it will make a new call frame and push it on the stack. That's why we saw that Stack Overflow with our infinite loop recursion we saw. If I do rec sum, this is what we're going to see on the stack. Well, we'll assume our main method is running and it calls rec sum. So perfect. We call with rec sum 5. And remember, the call frames also they know where to return to, basically like where to go after we pop. All the formal parameters, that's like the 5. All the local variables that exist in there, there's going to be none, so it doesn't matter. And actually, no, the n, because n is going to be equal to 5. So that's like the local variable. And also the return value. So rec sum knows that, although it doesn't know the return value yet, because it can't determine the return value until the recursive stuff has been done. Well, you'll see what I mean. So if I call that, then rec 4 is going to be called, because we're going to call it on n minus 1, and then on n minus 1 at minus 1, and then n minus 1 minus 1 minus 1, and then n minus 1 minus 1 minus 1 minus 1. I think I did that right. And then that'll return the 1, which then we know, okay, and then plus the 2, which is 3, plus the 3, which is 6, plus the 4, which is 10, plus the 5, which is 15, right? If we did it this way, okay, here's another view of it, right? So we push the 4, then the 3, then the 2, then the 1, but then we now know what to return, so we know that return value. And then we know the return value, then we know the return value, then we know the return value, and then it's 10 here, because this was rec sum 4, not 5 anymore. Now, notice how rec sum 5 would have made a call to rec sum 4. So, right? So if we call rec sum 6, we are going to inevitably call rec sum 5. Like, notice how the solution to rec sum 5 is needed for rec sum 6. This is what I was talking about yesterday. Like, oh, look, I know I didn't call recsum6, but if I was doing like recsum n, of n, and I had some arbitrary value k, which is known to be less than n, the solution to recsum k is computed here if k is less than n. That should make sense. Basically, in calculating recsum 5, we had to, like, we found out what recsum 4 was. So we actually know what the sum of all numbers from 1 to 4 is. So if someone wanted to know, like, imagine I just calculated, like, recsum 10, right? And then immediately after I call recsum 5, I will be doing, like, work I already did. Because when calculating recsum 10, I'd have to go all the way and calculate recsum 9 and 8 and 7 and 6 and 5, 4, 3, 2, 1. But then when I call recsum 5, I'm going to calculate recsum 5, recsum 4, recsum 3, recsum 2, recsum 1. All of which I had actually already computed up here, which is neat, right? So recursive things tend to be like Russian nesting dolls, you know? Okay, so just to note, there's a pretty interesting relationship between recursion and the stack ADT in general. Yeah. Okay, recursion just versus iteration. Just because we can doesn't mean we should. In practice, on the machines that we use today that we call computers, these things, I'm tapping my laptop, by virtue of how they operate, by like the mechanics, by the physical structure and the engineering that went into them, recursion's a little slow compared to iterative stuff. And that's because of the architecture we use, like because we have the call stack. Because every time we make a call frame, that takes time, that takes resources. We assign the values, we put it on the stack, then, you know, all that stuff happens, then we gotta take the call frame, remove it from the stack. That's a lot of overhead, where an iterative thing wouldn't do that. But just because recursion is slower than iteration on these types of computers doesn't mean that they are necessarily slower in general, if we kind of abstract away from these computing machines. And you got to remember, all of these algorithms that we're doing, like, if I gave you an algorithm to sort, if I told you how to do bubble sort, for example, a very simple sorting algorithm, you know, and you can code it up. But here's the thing. I could write those instructions down in English, line by line, kind of like a recipe, write them on like a whiteboard in a classroom, and sort students by height by following that algorithm. Except here, there is no computing machine. There is no like laptop running the code. It's like me and us executing it. And if I did bubble sort recursively, we could follow that algorithm and it would be no different. Except when we consider things like complexity. So if we have an order n thing that's iterative and something that's order n but recursive, the recursive one is going to be slow. Okay, I'll do the sad face there. So look how sad it is. But again, that's just by virtue of how this works. But then again, there are some implementations of these algorithms that, well, anything we do recursively, we can do iteratively and vice versa. And sometimes there are programs out there that are trivial to write recursively versus iteratively. Not necessarily that the iterative version of those algorithms are overly complicated. It's just that the recursive one is so easy. And Fibonacci is the classic, quintessential example of this. All right. The numbers in the following sequence are the Fibonacci numbers. Take a look at these numbers. Don't blurt it out loud. Take a look at these numbers and see if you can find the pattern. How does this sequence work? Why does 2 come after that 1? And why does the 3 come after that 2? Why does the 5 come after that 3 and so on? What's the pattern? Now, Look, Jared, what did I just say? I said don't say anything. Don't ruin the fun. Way to go. That's okay. You're absolutely right, Jared. It's the sum of the previous two numbers. Yeah, it's okay. I'm just teasing you. So 2 is 1 plus 1, right? 3 is 1 plus 2. 5 is 2 plus 3. 8 is 3 plus 5. 13 is 5 plus 8, and so on. So the number that comes after here would be what just happened? The number that comes after 89 would be 55 plus 89. Let's see if James can do arithmetic. I'm going back to grade 2. So 9 plus 5 is 14. That's 13, 144, right? Someone make sure I can do math, because we've already established we as a group cannot do letters. So hopefully we can do math. So take a moment and think about how you would implement this iteratively. Right? Like if I told you to code this iteratively, not recursively, iteratively, what would you think to do? And you know, it might be a good exercise. In fact, I'm going to give actually a minute or two to actually have you try this. How would you code this and get it working iteratively? You don't actually have to actually implement it, but just think of the idea in general. I'm going to give you a moment to think about this because this is a good exercise. So I'll shut up for a second, but don't worry, I'll go back to that. All right, what do we think? Like, raise your hand if you think you have an idea. All right, one person, two people, couple people. Here's what I think I would do. I mean, there are a lot of ways I could do it. Maybe like the laziest way. I don't know if lazy is the right word, but here's how I might do it. I'm gonna actually make like a list, right? And I'm going to put 1 and 1 in the first two spots. Like I'm gonna create a list, it'll be an empty list. And then do put like add 1 to it, you know, it'll go to the end. Then after that, I will just take the last 2 elements of the list. So maybe it's like an index list and I keep track of the size. So I can easily access the previous 2 things, add them together, and then append it to the end of that list. And put that in a loop to run till ever I want. That would totally work. I mean, perhaps a simpler one, because that'll make use of a linear data structure, which will take up space. And, you know, you could think, well, how much space will it take up? Well, it'll be like order n space, right? Because if I want to calculate the nth Fibonacci number, and I'm going to have a list of n things, I'm going to have to, like, keep that and store that somewhere. So the amount of space required would be, like, on the order of n. But I can do, like, a constant space algorithm where basically I just start with 2 variables. One called, like, m1, m2, right? Where m1 is like -1 and m2 is -2. So that'll be like the previous 2 ones. And then I'll do something like, okay, cur equals m1 plus m2. M1 equals cur. Actually, I should do M2 equals M1, and then M1 equals cur. And then just repeat that over and over and over again. Raise your hand if those were like more or less the ideas you had. One of the two at least. Yeah, cool. So that's like your standard way of doing it. Not overly difficult at all, but here's the recursive definition. Mathematically, at least, if you're asking for what the nth Fibonacci number is, so this is the first, this is the second, this is the third, this is the fourth, this is the fifth, this is the sixth, this is the 7th, 8th, 9th, 10th, 11th, and so on, assuming we start counting at 1, we would say fib 1 equals 1, fib 2 is 2. Otherwise, for any arbitrary n, it's just fib of n minus 1 and fib of n minus 2. So if I wanted to know like the third one, well, here's what I would say. I would say, okay, fib 3, well, that's equal to fib 2 plus fib 1. But, you know, we know what fib 1 and 2 are. That's just 1 and 1. There. That's it. And here's the code for a recursive Fibonacci. Look at that. If that doesn't excite you, if that doesn't get the hair on the back of your neck to stand up with how gloriously simple and elegant that is, I don't know what's wrong with you. This is just, oh, this is so good. This looks so good. I mean, I suppose I should say something like, well, if n is less than 0, because Fibonacci numbers are only defined for positive integers, I suppose, so I could do some error checking there, and it would make it a little bit more complicated. But let's not worry about that. Let's assume good faith by the person using this function. Look at that. Ah, that's glorious, right? So what does it say? Well, if n is 1 or 2, return 1. Otherwise, return the sum of fib n minus 1 plus fib n minus 2, right? Because that's what, like, if I am at the nth position, so here's the 0th one, actually I should start counting at 1, 2, 3, da 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 da. This is the n minus 1, n minus 2, right? And so fib of n, well, that's just the sum of the previous two. But how do you calculate this one? Well, that's the sum of this one and this one. And then this one's the sum of that one and that one, and so on and so on and so on and so on and so on. And here's the iterative one, right? I guess I'll say, like, okay, if n is 1 or 2, return 1. Otherwise, I've got like next, cur, and previous. This is what I called like M1. This is what I called cur, I guess, and this was M2. Start I is 3 all the way to n inclusively. Next is the sum of those two, set previous to cur, cur to next, right? And in the end, return next. There. Basically what I just explained a moment ago. Now, obviously this is not an overly complex algorithm, right? It's not scary. When you look at that, maybe you couldn't come up with this on the top of your head in the 2.5 minutes I gave you to think about it, which is entirely reasonable. But when looking at this code, you would say, yeah, there's nothing crazy going on here, nothing crazy. But if you ask me, that's a lot. Like, look at that. That's glorious. Where this, you know, there's nothing wrong with it. You know, I guess it'll get me out of bed, but this really excites me. This makes me want to get out of bed. So what did I hear? In the recursion, doesn't the use numbers and not the list numbers? In the recursion, doesn't that use numbers and not the list numbers? I'm not list indices. What? Yeah. So, well, but like the nth one. What? So I mean, we're not using list indices here in this implementation. We could do the list one where we just make a list and append two things instead. I'm not sure what you're asking though.
Like for, like in the slides, like n minus 1. If n is 1, or sorry, if n is 3, because it would have broken if it was 1, wouldn't that just be, oh, fib of, like, we're not actually accessing the fib number, we're accessing, like...
Remember, this is a function.
Yeah.
So we're calling the function. So we'll just go here and be like, oh, well, what's fib? If we put in 3, we have to calculate what fib of n minus 1 is, which is 2, fib 2. Oh, that's just 1. So I'll return 1. And then fib of n minus 2, well, that's 3 minus 2 is 1. So what's fib of 1? Oh, well, that's just 1. So fib of 3 is equal to 2.
Oh, okay.
Does that make sense? That's like what we did here too. Done. So take them in and make sure this makes sense. Yeah, well, whatever. So, which one looks easier to implement? I don't know about you. I like this one. I like it. Oh, it's glorious. This one, again, not bad, but I like the recursion one. Now, though, we know that in practice the recursion is slow on our computing machines that we program on, but let's ignore that for a second and assume we've got humans doing the computation in a room on a whiteboard or something, and they're just following the steps of the algorithm. So, what is the computational complexity of this algorithm? Take a second, look at it. Don't type anything in the chat, though. I'm looking at you, Jared. Don't type anything in the chat, though. And then after a minute, I'll have everyone who's figured it out to tell me what the big O is of this function. But don't say it yet. I'll give you a couple of seconds. All right, what do we think? One answer. It is n. All right, 2 answers, and yes, it's n. It's linear. Why? Well, here, if I'm calculating the nth one, right? Well, I'm gonna have to calculate. So I've got 0 and 1, but then I gotta calculate the 3rd, then the 4th, and the 5th, and the 6th, and the 7th, to the nth. So I'm gonna have to look at all the ones from 3 to n, right? Which, well, that's just order n. Now, what the heck is the computational complexity of this one? And I know I've never shown you how to calculate, well, I showed you how to calculate computational complexity, but usually the rules we were following up until this point was, you know, you kind of look for the loops and whatnot, right? But here, like, we can't look at a for loop, but it's not obvious. But the same rule applies. Like, if you call this function with some arbitrary value n, how much work is being done in relative to the value n? So I'm going to give you like a minute to look at this. And I'm going to time this. I'm going to give you a minute to look at this. Maybe I'm even going to give you a minute and a half. And I'll have you try to figure this one out. See if you have any idea how on earth you can figure out the computational complexity of this right here. I'm going to start my timer. Okay, I'm going to give you a minute and a half. Well, I'll mute myself quickly. Do we have any ideas at all? N squared, 2 to the n, 2 to the n. Well, let's talk through this, because 2 out of 3 of you are right. And we'll talk about it. So, I have a feeling, though, all 3 of you were thinking the same thing, but maybe you just kind of got the math backwards or something. But you're absolutely right, and it's actually fascinating. Now, you got to tell me, were you already kind of familiar with this, or did you Google it or something and try to impress me? Or, oh wait, no, only 1 of 3 of you is right. Ooh, interesting. Now, I didn't say it was you. How'd you know? Did you actually like calculate it, or did you just kind of, you know already, or you've seen it before? There are 2 things for every n. Exactly. There are 2 things for every, well, actually each function calls has 2, which calls 2. Yes. So that's Alex, you are 110% correct. And Johannes, you have the right idea too, but I'm just going to rephrase what you said just a little bit. In fact, let's see. Okay, I don't like these slides. So I'm going to actually just draw this paint. So when we look at this code here, we clearly see, I'm just going to make this bigger, that, look, like the amount of work being done, like in here, is like order 1, right? Like there's nothing extra taking place here, right? For every function call, like it's a constant time amount of work. Because this is constant time, return 1, constant time, return. Look, if I know the value of fib n minus 1 and fib n minus 2, it's constant time to just add them together and return it. So the question then becomes, okay, if I know it's constant time for every time this function is called, now we need to ask the question, how many times is this function called? So let's think about it. If I'm going to do it with like, okay, if I call this function with some arbitrary value n, okay, I'm going to make a function call over here for n minus 1, and then a function call for here, n minus 2. But then the one for n minus 1 needs to make 2 function calls, which is going to be n minus 1, which is n minus 2. And then over here we have one for n minus 1 minus 2, which is n minus 3. And then this one we have n minus 2 minus 1, which is n minus 3. And then over here we've got n minus 2 minus 2, which is n minus 4. And then over here, well, we're going to have 2 function calls, which will be n minus 2 minus 1, which is n minus 3. Then over here, n minus 2 minus 2, which is n minus 4. And then n minus 3 minus 1, n minus 4. And then over here, we've got n minus 3 minus 2, n minus 5. And then here we have n minus 3 minus 1, n minus 4. And then over here, we've got, what do we got here? We've got 3 minus 2 is n minus 5. And then here we've got n minus 4 minus 1, which is n minus 5. Then over here we've got n minus 4 minus 2, which is n minus 6, and so on and so on and so on and so on and so on. But Alex was right. Look, every time when we have, here we have 1 function call, then 2, then 4, then 8. 1, 2, 3, 4, 5, 6, 7, 8. How many do you think would come after the 8? 16. 32. So every time we're doubling, so this is 2 to the power of n. So this is big O, 2 to the n. I hear a boop. Minecraft, each function, why Minecraft big O? What? So n squared, which is crazy. So this is growing by factors of 2. Now you might say, well, hold on. Like if I did something, I'm going to get rid of this. And what if I put in like 4? No, I did 4. Let's do 5. So here we would have 5. We would have 4 and 3. And then here we have 3 and 2. And here we've got 2 and 1. Maybe this is a bad example because... Oh, and then over here we've got 2 and then 1, right? That's a 2, trust me. Right? So you'll say like, well, hold on. Not everyone is doubling because like this is an uneven tree. And if I had this to be 6, you would kind of see how like it gets even more uneven as n gets bigger and bigger and bigger. But in our quick and dirty computational analysis, computation complexity analysis, we're looking at n squared. Now, let me ask you, super important quiz. What's worse? To have an algorithm that grows linearly or have an algorithm that grows exponentially? Exponential sucks. If you have a choice between 2 algorithms that do the same thing and one's linear and one's exponential, do the linear one. Don't even think, don't even consider doing the exponential one. That is disgusting. In fact, if we go wiki complexity and we find the table of like, oh, you know, common complexity values. Oh, I guess I have to do like big O notation. So at the bottom of our list, we have like constant time, but then close to the bottom of our list, you know, I guess it's not that close, but something linear, linear's good. And then we have all our polynomial time stuff that comes after the n log n stuff. But look, some constant to the power of n, the exponential, is like, it's like some of the worst you could ever have, okay? So don't do recursive Fibonacci. Now, you might be then asking yourself, well, hold on, but the recursive Fibonacci was so nice. It was beautiful. But it took 2 to the n. It took 2 to the n steps to do it. Why though? Like, why is the iterative one? Now, remember, we're not talking about the fact about iteration being faster on these computing machines. We're talking about the algorithm's computational complexity. So why is this strategy right here that we're looking at? Let's see, can I just undo everything and go back to what we had? Yes. Why is this strategy so horrible compared to the other one? If the iterative one was linear time, and this is exponential, what makes this exponential? Why is this not the same? Like, what makes this algorithm so bad? Can anyone see? I guess my head's in the way to see the 32, but here, I'll just, there. I don't know which way I need to go to hide. But what do we think? Why? Any ideas on, well, any ideas on why? Oh man, I did not know about GTA 5. Is that why online loading took forever? Huh. Why? It makes 2 calls to check any one number. Well, yes, you're correct, but that's not the explanation I'm looking for here. Like, you're right, but what is it about this algorithm that makes it so much worse? Like, yes, it's making 2 calls, but that's really not what I'm looking for. I'm looking for a more intricate answer. And I'm going to go back to this picture here that we drew. And I'm going to hide. Well, here, I can hide by turning off this. There. So what about this is so bad? Look at this here, and can you see any interesting pattern? It doesn't store the numbers we've done, so it calculates some twice. You're absolutely correct. In fact, it's worse than that. we're not just going to calculate things twice. We're going to calculate things so many times. Like, how many times have we calculated n minus 3? Look, in this example, we calculate n minus 3 once, twice, 3 times. Here, we've got n minus 4, n minus 4, n minus 4, n minus 4. My goodness. So, like, sure, we calculated n minus 2 and n minus 2 only twice. But, I mean, if I kept going down, we're just repeating more and more and more and more and more work that we've already done. Where the iterative one, it never did. It never calculated, well, what is fib n minus 3? It only calculated fib n minus 3 once and only once. Where here, it's going to calculate it some hilariously large amount of times. Well, actually, no, I shouldn't say that. N minus k, where k is some number between 1 and n. N minus k, it's going to calculate that some hilarious amount of times. And that's bad. That's really bad. So this one's doing a lot of duplicate work. Now you might say, okay, could we create like a lookup table then where every time we calculate it, like we add it to like our lookup table? And yeah, we could totally do something like that to solve this problem. But the pure, absolute, like, look, how sad am I now? My beautiful, exciting, gets me out of bed in the morning, hair on the back of my neck stands up algorithm actually is terrible. Can't we just write the for loop from the iterative into recursion? I don't know if that would be the best way to go about fixing it. I think it would just be easier to create some like global, like data, like a global list that just stores values that are already there. And every time we look to do like n minus some arbitrary value, check to see if it exists. If it does, great, use it. Otherwise, do the calculation. And that should make it much better. Although we would still have to do extra work, but still. There is a way to make the recursive version just as optimal as the iterative one, but not with a solution that looks this good. So, yeah, and here's me drawing it with fib 6. And like, look, again, look, if we're doing fib 6, we're calculating fib 3, fib 3, fib 3. You know, fib 2 is getting done here, 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 fib 2 got done here. And I know each one of these is constant time, but I have to answer that a lot of times. Now, we won't have time to do Towers of Hanoi. All right, we'll pick up here next time. Yeah, ooh, how much longer is left? Okay. I will say here, I'll end with this. You know, you might say like, well, you know, recursion, it's, I don't know, I like iteration better. Recursion's yucky. But here's the funny thing about recursion. Within our universe, a lot of systems, a lot of processes that exist within our universe achieve looping, achieve repetition through recursion, not through a for loop. There's going to be chemicals that work in a certain way. There's going to be vegetables that grow based on how it grew before, and then create these like interesting fractal designs, you know? The way like, I think that's like ice on Mars or something. And this is the way like, I don't know, something happened. And the way ice is starting, you know, it crystallizes and kind of sometimes will create these funny, like, interesting fractal-like thing. It's just by the consequence of how our universe works in these structures. So a lot of times, well, recursion is actually arguably a much more natural form of repetition compared to iteration. Now, we will do Towers of Hanoi, because Towers of Hanoi has a beautiful little story that goes with it. But we'll do Towers of Hanoi on Friday. But for the most part, like we're done recursion. Towers of Hanoi, I'm just showing you because it's got a fun story. Anyways. Ooh, actually, no. Here, we've got so recursive sum. No, we'll do this next week. or on Friday too, where we'll do some computational complexity analysis of recursion again, but with simpler functions. Towers of Hanoi is bad, by the way. Anyways, any questions before we wrap up? All right, seeing none. Awesome. Everyone, enjoy the rest of your day, and I'll see, I think, at least one of you tonight in 2:15.